Assalamu alaikum. It is the lecture 13 of data security and encryption and part 2 of Advanced Encryption Standards lecture, and we are continuing from the previous lecture where we have left on the light slide. So here are the lecture contents. In this lecture we are going to discuss about advanced encryption standard, key expansion techniques and its algorithm, and rationale for key encryption expansion. Then an AES example will be discussed along with an avalanche effect, and finally we will discuss some AES implementation and equivalent inverse ciphers and some implementation aspects. So AES key expansion, as discussed in the last slide, takes an input of 4 words, 16-byte key, and produces a linear array of 44 words, 176 bytes. So this is sufficient to provide a 4-word round key for initial add round key stage and each of the 10 rounds of the cipher. So key is copied into the first 4 words of expanded key. The remainder of the expanded key is filled in 4 words at a time. So each added word WFI depends upon the immediately preceding words WFI-1 and the word 4 positions back, i.e. WFI-4. So in the encryption process, at each step, the word I is combination of 4 words previous to that. So in 3 out of 4 cases, it is a simple XOR operation. For a word whose position is W array is multiple of a 4, a more complex function is used, such as for the position of 4, 8, 12, if the key is more than 12 words long. So this figure illustrates the generation of the expanded key using the symbol G as depicted here to represent that the complex function. The function G consists of number of subfunctions. First of all, it consists of a root word function that performs a 1-byte circular left shift on a word. That means an input word, if we say we have a word called W0, W1, W2, W3 is transformed into W1, W2, W3 and W0, thus performing a 1-byte circular left shift. The second subfunction is subword, and it performs a byte substitution on each byte of its input word using the S box as depicted earlier. So as you can see, the words are uh, left shift in the first step, and then the resulting words are substituted with the X box. The result of these two steps is XOR with a round constant known as RC. The round constant is a word in which the 3 rightmost bits are always 0. Thus the effect of XOR is a word with the OR con is the only perform an XOR on the leftmost byte of the word, which is represented as RC of J. The round constant is different for each round and defined as OR constant J is equal to OR constant J, 0, 0, 0. So it implies that the round constant of round 1 will be 1, 0, 0, 0, which will be resulted of only one bit of RC is equal to 1. So we can calculate the any number of any rounds round constant as the equation RC of j is equal to 2 dot rc of j minus 1. So multiplying with the previous round constant with the 2 will get you to the any round constant for the next step. And with multiplication defined over the field g of f2 raised to power 8. So the Rindal developers designed the expansion key algorithm to be resistant to non-cryptanalytic attacks. That means it is more resistant if the user is able to get some information of your cipher key and wants to guess the remaining information. So the inclusion of round dependent round constant RCFJ eliminates the symmetry or similarity between the ways in which the round keys are generated in different rounds. So the specific criteria for these round dependent round constants are given as under. So it states that the knowledge of a part of a cipher key or round key does not enable calculation of many other round key bits, because at each step you use a different key expansion word to actually cipher or encipher the plain text. Then it is an invertible transformation, that means knowledge of any number of consecutive words of the expanded key algorithm enables regeneration of entire expanded key. So it was a speed on a wide range of processes, and it used a round constant to eliminate symmetries. Then there is a diffusion of cipher key differences into the round keys, that is each key bit affects the many round key bits, which we will see shortly, and enough non-linearity to prevent the full determination of round key differences from the cipher key differences only. And there is simplicity of the description of expansion algorithm, and it is very useful. However, the authors of these specific criteria in the first point of the preceding list do not qualify or quantify the statements. But the idea is that if you know that there is number of consecutive words of either in the cipher key or one of the round keys, then it is very difficult to construct the remaining unknown bits. In other words, the fewer bits one knows, it is more difficult it is to perform the reconstruction or determine other bits in the key expansion. So let's look at an example of Advanced Encryption Standard key expansion algorithm. So we'll consider some of its implications. Although you are not expected to duplicate the example by hand, you will find it informative to study the hex pattern that occur from the step to the next step. So for example, we have a plain text in a hexadecimal form. This table shows the expansion of 16-byte key into 10 round keys. As previously explained, this process is performed word by word, with each 4-byte word occupying one column of the word round key matrix. So the left hand column shows keywords, which is a 4 round keyword generated for each round, and the right hand column shows the steps used to generate the auxiliary word used in the key expansion. So let's begin with the key itself serving the round key for the round 0. So we have a number of words for the round 0, that is W0 to W3, that is equal to 4 words, and each word contain 4 values of 1 byte each, that will be equal to 4 bytes, and 4 plus 4 will be equal to 16 bytes. So as you can see, we have first method called rot word. route word performs a 1 byte circular left shift on a word. This means that the input word will be translated one shift to the left. So we have taken W3 as route word and performed one shift left. So the first statement is 7F, next is 6798, and the first AF is translated to the lost. Then the next method, subword, is performed by a byte substitution on each byte of its input word using an S box. So for example, we have performed an S or subword on X1, and it is a value from our initial plain text, which is given the value of Y1. The initial value was given X1. And then we have the value of the round constant or con, which was equal to 100 for the first round, and then we perform the operation y1 and XOR with the round constant 1, and we get the value z1 in our first step. So algorithm works repeatedly in each step and generating a sequence of steps to generate a ciphertext. So as you can see in the final steps, we have get to the y10 and performed with the round constant of round 10, and finally get out the value of z10. So this example shows the progression of state through the AES encryption process. The first column again shows the value of the state at the start of the round. For the first row, state is just a matrix arrangement of the plain text. The second, the third, and the fourth column show that the value of the state for that round after the subbyte, shift rows, mix column transformation respectively. The fifth column shows the round key. The first column shows the value of state resulting from the bitwise XOR or of state after the preceding mix column with the round key of the preceding round. So initially we have the plain text and the round key, and after uh, implementing round key in the first step, we can perform the substitution, then we perform the shifts, and then we perform after mix columns, and finally again it is implemented with the round key. The step is repeated 10 times, and finally we get our cipher text. So in the data encryption standard, we studied a change effect which was known as avalanche effect. The avalanche effect is also visible in the advanced encryption standard, and we can see change in the plain text. So if a small change in the key or the plain text were to produce a corresponding small change in the ciphertext, this might be used to effectively reduce the size of plain text or key space to be searched. However, it is desired that the avalanche effect, in which a small change in the plain text or key produces a large change in the ciphertext. So in this example, the second column shows uh, the value of the state matrix at the end of each round for the two plain text. Note that after just one round, 20 bits of the state vector differ uh, from two plain text. So after two rounds, close to half of the bits differ. The magnitude of difference propagates through the remaining rounds. A bit difference is approximately half the position in the most desirable outcome. So as you can see, after the round 2, we get approximately around 60 to 65 bit difference in after each round. So if it is not a best practice to change more than half bits. Clearly, if almost all the bits are changed, this would be logically equivalent to almost none of the bits being changed. Put another way, if we select two plain text at random, we would expect the two plain text to differ in about half of the bits position, and two ciphertext is to also differ in about half of the positions. Similarly, a change in the key also produces avalanche effect. The change in the state matrix values when same plain text is used and two different keys in the 8 bits are used. Again, when one round produces a significant change uh, and the magnitude of change after all subsequent records is roughly half of the bits. As you can see, after the second round we have more than 58 bits of difference, and it is almost about half of 128, around 64 bits on average. Thus, based on this example, Advanced Encryption Standard exhibits a very strong avalanche effect. However, if you recall the data encryption standard, the avalanche effect is stronger here than the data encryption standard, which requires 3 rounds to reach at a point at which approximately half of the bits are changed. So both for a bit change in the plain text and a bit change in the key. So AES decryption cipher is not identical to the encryption cipher, as we discussed that the encryption and decryption programs in AES differ from each other. So the sequence of transformations differ, although the form of the key schedules is the same. That means you can use the same expansion keys or round of keys, but the sequence of transformation is different. So it has the disadvantages that two separate software or firmware modules are needed for applications that require both encryption and decryption. So it has been discussed a couple of times now that you will require two softwares or two applications, one for the encryption and the other for the decryption. However, the key mechanism and the key expansion rounds are similar for both of the softwares. However, they are not completely very different software. They are almost equivalent versions of each other but in the opposite direction. The equivalent versions has the same sequence of transformation as the encryption algorithm, with the transformation replaced by the inverses. To achieve this equivalences, a change in the key schedule is needed. So in this case, you have to two separate changes are needed to bring decryption standard structure in line with the encryption structure. So the first uh, change is that the first two stages of the decryption round need to be interchanged. For example, in encryption round, the structure of sub-byte was performed first and shift rows were performed second. And in the decryption side, you will perform the shift rows first and then you will perform the sub-bytes. That means you will interchange the first two processes. That means in the decryption process, the first step will be invert shift rows and the second process will be invert substitution bytes. Similarly, the second two stages of the decryption round need to be interchanged. That means in the encryption process you had the mix column at the third step and add round key at the fourth step of each round. So these two steps must be replaced in the decryption process, and you will have the inverse sub bytes in the third inverse add round key in the third step, and inverse mix column at the fourth step. So put in the simple words, the first and second process of encryption in each round must be interchanged, and third and fourth process in the encryption process must be interchanged, and in this way you can perform the decryption. So interchanging inverse shift rows and inverse sub bytes affects the sequence of bytes in state, but does not alter the byte contents and does not depend on the byte contents to perform its transformation. Inverse sub bytes affects the contents and bytes in the state, but does not alter the sequence and does not depend on the byte sequence to perform its transformation. Therefore, these two operations commute and can be interchanged very easily. Similarly, interchanging add round keys and inverse mix column is also very easy. The transformation by add round key and inverse mix columns do not alter the sequence of bytes in the state. So if we view the key as a sequence of words, then both add round key and inverse mix columns operate on the state one column at a time. So these two operations are linear with respect to column input. So therefore there will be no change in the state of the actual values, but only in the position of our state matrix. So as described earlier, this example illustrates the equivalent decryption algorithm. That means we have input as the ciphertext here, and then we perform the decryption process. So we can interchange the add round key and inverse mix column, provided that we first apply the inverse mix column to the round key. Note that we do not need to apply inverse mix column to the round key for the input to the first add round key transformation preceding the first round, nor to the last add round key transformation in the round 10. So as you can see, we have the add round key as the first step, and then we perform inverse sub bytes and inverse shift rows, and then inverse mix columns and add round key. Similarly, in each step we repeat the same sequence, and at the end we get our plain text. So this is because the add round key transformation are not interchanged with the inverse mix column to produce the equivalent decryption algorithm. So AES can be implemented very efficiently on number of processors, and it provides some suggestion for efficient implementation on 8-bit processors. So typically for current smart cards, and it works on the 8-bit processors, and for 32-bit processors it typically works on personal computers. So AES can be implemented very efficiently on 8-bit processors because it uses the 8 bits to represent one element in a state. So add round key is a bitwise XOR operation. Shift rows is a simple byte shifting operation. Sub bytes substitute bytes operate at the byte level and only require table of 256 bytes. So mix column requires the matrix multiplication in the field of GFF to raised to power 8, which means that all operations are carried out on bytes. Similarly, AES can also be efficiently implemented on 32-bit processors, and it defines steps to use 32-bit words, and it can pre-compute the 4 tables of 256 words. Then each column in each round can be computed using 4 table lookups plus 4 XORs, because we are using the 4 tables in the 32-bit. That means 4 tables of 8 byte each. So at a cost of 4 KB to store tables. So designers believe that it is very efficient implementation and was key factor in its selection as AES Cipher. So that concludes the AES topic, and in this lecture we discussed about the AES key expansion algorithm and its rationale, and finally we described an equivalent inverse cipher or decryption algorithm for AES and discussed some implementation aspects on 8-bit processors and 32-bit processors. If you want to read more, you can look at the chapter 6 of the recommended book, and you can ask me through the question and answer session or any other medium. Thank you very much.